Okay, welcome. In this lecture, we're going to cover an exciting topic, which is memory consistency. This is an issue in multiprocessors as well as distributed systems. In this talk, we'll talk about the issue within the context of multiprocessors. But keep in mind that, in general, whenever you have distributed systems with multiple different processes potentially operating on shared data, you run into consistency issues, and different views of data need to be kept consistent for correct execution. And that's the problem we're going to cover. And this is an exciting area. This is a tough area. I'd like to encourage you to actually read other papers related to this topic if you're interested, and I'll recommend some papers, and I'd be happy to give you more papers as well. Well, speaking of readings, there's only one required reading, which is Leslie Lamport's seminal paper, which is actually only 2 pages. You can see that this is page 1 and this is page 2. It's actually less than 2 pages. It's How to Make a Multiprocessor Computer That Correctly Executes Multiprocess Programs. That was written in 1979. And this introduces the idea of sequential consistency, which we will cover quite a bit today. And there are a bunch of recommended readings over here, and this is just a partial list. I'm happy to provide more readings, as I said. These are readings that actually introduced weak consistency models, relaxed consistency models by Koroshgar-Chorlu, as well as techniques to enhance the performance of some of these memory consistency models, and a recent reading by Louis Cezé on how to actually enforce consistency at coarser grain intervals, coarser grain chunks of instructions. Okay, before we start on consistency, just a brief review of what context we're going to cover in this lecture. We're going to talk about multiprocessors. And remember that we've covered loosely coupled and tightly coupled multiprocessors, and the basic difference between these two models is the existence or the lack of a shared memory address space, shared global memory address space. In loosely coupled memory multiprocessors, there is no shared global memory address space, so this is more like network-based multiprocessors. Consistency issues arise in such processors as well, because these processors can actually share data, not necessarily address space. Tightly coupled multiprocessors share the global memory address space, and basically consistency issues arise here too. Maybe there are different kind of consistency issues, though. One is based on shared data and the other is on shared memory addresses. But you can share data without having a shared global memory address. Okay. This we have covered early on in multiprocessing basics, so I'm not going to go over this in more detail. But a lot of the discussion that I will assume in this lecture will be based on the shared global memory address space processors, where you have shared memory across different processors. Which means that when you're manipulating shared data, you will require synchronization from these different processors, some kind of lock or barrier or some kind of synchronization construct. And we'll see that a lot of the consistency issues arise when you have these shared variables. Okay, there are some main issues in tightly coupled multiprocessors. Shared memory synchronization, which we've been talking about in some of these lectures. Cache consistency, which we will cover. And ordering of memory operations is the subject of this lecture. What should the programmer expect the hardware to provide? And there are a bunch of other issues: resource sharing, communication, and load imbalance, which we've been covering in this course. One caveat of parallelism, remember Amdahl's law, serial bottleneck is an important caveat, but there are also bottlenecks in the parallel portion, which are synchronization overhead, load imbalance overhead, and resource sharing overhead. Basically, even if a program is designed to be parallel, there are parts of the program that are serial. That's Amdahl's serial bottleneck, and you read this paper, Amdahl's law. If you haven't, I would strongly encourage you to read it right away. And that reduces your parallel speed up. But also the parallel portion is not perfectly parallel, because you have several overheads due to synchronization, shared data updates, load imbalance, and resource sharing. And we've covered this early on. And these are the overheads that make it difficult in programming, especially bottlenecks in parallel portion. And we're going to consider the issues in parallel portion in this lecture. Basically, operations manipulating shared data cannot be parallelized. That's the problem. So you need synchronization. And this requires locks, mutual exclusion, and barrier synchronization, condition variables potentially. This leads to communication. Tasks may need values from each other. And this communication is accomplished through a shared global memory address space in a tightly coupled multiprocessor. The problem is this causes thread serialization when shared data is contended. So programmers would like to reduce this. And we will get back to this in the next slide. This is a tough problem. It's not easy to reduce synchronization or the amount of synchronization that happens, because then you run into correctness problems if you actually do something wrong, if you do not synchronize on some of the shared data updates or reads. The second issue is load imbalance. Parallel tasks may have different lengths, and we've talked about this. And if you want to remember, if you want to brush up your memory, you can take a look at the parallel task assignment lecture that we put up for 740. This happens due to imperfect parallelization or microarchitectural effects, as we have discussed, or data dependence effects, as we have discussed. This reduces speed up in the parallel portion. So you would like to reduce load imbalance as much as possible also. Resource contention. Parallel tasks can share hardware resources. As a result, they can delay each other. And this happens because replicating all resources in the system is expensive. And this leads to additional latency that's not present when each task runs alone. In this discussion, we'll mainly focus on synchronization. And actually, memory consistency issues arise because there's synchronization that happens on shared data. And I'll give you an example that's similar to Decker's algorithm that's used for synchronization. And we'll see a violation of correctness if you do not have memory consistency. Good memory ordering good ordering of memory operations from different threads, different processors. So the difficulty in parallel programming is really in two things. One is getting parallel programs to work correctly, and the second is optimizing performance in the presence of these bottlenecks, in the presence of shared data updates, mutual exclusion requirements, in the presence of load imbalance, and in the presence of resource contention. And it's much of parallel computer architecture is about, as we have discussed earlier, two things. One is designing machines that can overcome these bottlenecks to achieve higher performance and efficiency. And the second is making programmers' job easier in writing correct and high performance parallel programs. And both are important. How do we enable the programmer? Well, both of these are important. First, how do you design machines that reduce these bottlenecks such that the programmer doesn't do much? So that actually amounts to making programmers' life easier. But also, there's another aspect. How do you actually design the primitives such that the programmer is more easily writes correct and high performance parallel programs? So in this lecture, we'll focus on the second one. Memory consistency is all about how to make programmers' life easier and also achieve high performance at the same time. And you can actually achieve a trade-off between making programmers' life easier in reasoning about parallel programs or getting higher performance. So this trade-off is interesting. Once you make programmers' life easier, you need to support this in hardware, which leads to hardware designers' job to be harder, as well as potential opportunities for performance improvement to be less. And we will see this within the context of memory consistency models. And this is a classic example that an architect of an architect's choice. Basically, a computer architect usually makes a choice, a trade-off between the programmer and the microarchitect. Basically, if you want to make programmers' life easier, it usually makes the mechanisms you develop usually make microarchitects' life harder, because it takes more effort to implement those mechanisms in the architecture as well as microarchitecture. On the other hand, if you want to make microarchitects' life easier, then it's difficult. Then programmer's job usually becomes difficult. I'll give you two examples. One is single core versus multi-core processors, right? Do you design a faster, ever faster single core processor, or do you actually punt and design simple multi-core processors? And if you do a single, like a very fast, beefy single core processor, that's good for the programmer. The programmer doesn't need to optimize their programs as much. They don't need to write parallel programs, which is tough. That's harder for the microarchitects. Why? Because it's harder to design a single core, as we have discussed in an earlier lecture. On the other hand, if you design a multi-core processor, now this is easier for the microarchitect, well, assuming that you actually tile wimpy cores, right? This is the simple core approach. Because microarchitect doesn't need to design a single core, they just need to tile these multiple cores and somehow the hope is that the rest of the system is easier to design than designing a very beefy single core. But this makes the programmer's life harder. Why? Because now the programmer, to get the same performance, they need to parallelize their program on this multi-core system. Okay? This is a classic example. There are many, many examples in computer architecture. I'll give you one more example, and the idea is virtual memory support. Do you actually have a memory management unit that does transparently provide virtual memory, versus basically you expose the physical memory to the programmer, and I'll call this overlay programming. Basically, programmers somehow manages physical memory themselves, and this used to be the case early on. The programmer needed to actually use overlays, or the system needed to use overlays to actually manage memory, physical memory. So the idea of virtual memory is, in architecture, is to give the illusion of infinite physical memory to the programmer through the ISA as well as hardware mechanisms. Obviously, this is great for the programmer, right? The programmer doesn't need to worry about, am I running out of physical memory space? I have 2 kilobytes of DRAM. Well, 2 kilobytes is small, but it used to be the case at that time. 2 kilobytes of memory in the system. What happens if I run out of space? Well, then the programmer needs to write their code such that it fits mostly, right? If it doesn't fit, then the programmer needs to use either system functions or their own functions to bring the data from the disk all the way into memory. That's the idea of overlay programming. So virtual memory is good because it makes programmers' life easier. And that's one of virtual memory's biggest benefits. On the other hand, this makes microarchitects or architects' job, I'll do this, harder, because now you need to provide provide for the illusion. You need to do all that management of physical memory underneath, under the cover. Basically, you need to do demand paging. You need to accelerate these operations. Once you have virtual memory, you need to somehow make sure the loads are fast. How do you do that? Well, you have translation look-aside buffers in hardware. Some processors today, as we've discussed in 447, have page walking in hardware. Basically, all the way the translation steps happen in hardware. So a microarchitect's life is harder here. On the other hand, if you do not have virtual memory, programmer's life is harder because now they need to manage physical memory. But microarchitect's life is easier. Microarchitect can say, oh, there's no translation, and I'm not going to add these TLBs. I'm not going to have the page walk in hardware, and somehow the programmer will all manage it. So this is a very classic trade-off that we have in systems today. And you can actually add many more. In fact, one of the earlier questions that we asked in this course and other courses that are similar in computer architecture is, why don't you list some of the programmer versus microarchitect trade-offs that you've learned in this course? And you can come up with many, many different types of trade-offs. And one other example I'll give you is caches versus scratchpad memory, right? Which one makes programmers' life easier and microarchitects' life harder? Well, caches make programmers' life easier usually, right? Because they automatically cache the data, improve performance transparently. Scratchpad memory, the programmer somehow needs to figure out where to place the data, which data to place in the fast memory and which data to place in slow memory, and how to coordinate that data movement instead of hardware automatically figuring that out. Okay, basically what we will discuss today is also about making programmers' life easier in writing correct and high-performance parallel programs. And the idea is memory consistency. And let's take a look at this. Do you actually provide sequential consistency versus not? I'll make it not, and we'll go into more detail later on. Basically, providing sequential consistency, some sort of guarantees on the ordering of memory operations across different processors, makes programmers' life easier, versus doing not makes programmers' life harder. But we will also see that this makes hardware architects' life harder. Okay, so let's jump into memory ordering in multiprocessors, which what sequential consistency is all about. Basically, let's assume that we have operations A, B, C, D, and the key question is, in what order should the hardware execute and report the results of these operations to the programmer? This is essentially a contract between the programmer and the microarchitect. And this is specified by the ISA, instruction set architecture of the computer. Why is this important? Because preserving an expected, or more accurately, agreed upon order simplifies the programmer's life, and we will see this. Why? Because it leads to ease of debugging. Basically, the programmer can, if there's a agreed upon order, the programmer can debug the program much better because there's an expectation of an order. Whereas if the order is random, then it's going to be tough, right? And we've seen this in 447 when we talked about precise exceptions, right? Precise exceptions in a single core processor say that all of the operations until this point, which is the precise exception point, are done, and none of the operations have started. And that's the abstraction shown to the programmer. So you know exactly what operations have completed and what operations have not completed. It's not, there's that sequential order that's provided with precise exceptions, and that makes debugging really easy, right? Because you know exactly when a program is stopped, which operations are complete and which operations are not complete. That's the von Neumann model, right? This also eases state recovery. For example, when there's an exception in the program, if you have a good ordering contract between the programmer and the microarchitect, then what you can do is you can easily recover from an exception because you know exactly what is the state of the processor at that point in time. And this is true in a single core processor because you have a single von Neumann model. Basically, every instruction is executed sequentially, serially. Only one instruction is executed at a time. That's the abstraction provided to the programmer. And this expected order simplifies programmer's life. The problem is preserving this expected order usually makes the hardware designer's life difficult. And this is especially true if the goal of the hardware designer is to design a high-performance processor. For example, before we've seen that even though we have von Neumann model sequential execution as the abstraction provided to the programmer, to design a high-performance processor, you really need to execute instructions out of order to tolerate long latencies, right? So what does it take to execute instructions out of order? Basically, you buffer instructions into the future, right? What does it mean? Basically, you have this buffer through which you determine whether or not instructions can execute based on their data dependencies. Now, this buffer also contains loads and stores, right? As we've discussed in 447, if you want to execute instructions out of order, there are loads and stores in these instructions queue also. So, and you would like to preserve the order that's reported to the programmer in terms of these loads and stores. Let's say you have an out of order processor, you have this load, add, I don't know, multiply, store, load, and let's stop here. Let's say this gets a very long latency cache miss, and you're executing this program out of order, and you have a store over here and a load over here. Somehow you need to determine whether or not you can execute load out of order with this store, right? Can you actually execute this earlier? Well, if you're actually buffering instructions, you need to somehow buffer instructions such that you have stores here and loads here, and this load needs to somehow check whether the addresses overlap, right? You can potentially execute this out of order if the addresses do not overlap. So how do you check if the addresses do not overlap? Well, because you're executing instructions ahead, stores in program order, write their addresses and data in a hardware buffer, and their sequence number, I should say, in a hardware buffer called the store queue or store buffer. And when a load has its address ready, what it does is it searches this buffer and searches it with its sequence number to find out if there is a store that is writing to this address, right? If there is a store that is not writing to this address, now this load can load the data directly from the cache. Now if there's a store that's writing to this address, if there's a store that's writing to X, now the loader needs to ensure that that store is older, and if there's an older store that's writing to that address, this buffer provides the data of that store, right? If the data is available. If the data is not available, then now you have a scheduling issue, right? Basically, the load needs to wait, or you need to predict the value of the load. So that's the difficult part of designing a processor that can execute operations out of order. but the processor needs to report the results as if they were executed in order, right, to satisfy the von Neumann model. So to ensure that, you need the store buffer, and this store buffer is complex, right, because now whenever a load executes, you need to search the store buffer, its content addressable memory. And this search is not easy because you need to check if the address matches, and you need to check if the sequence number of the load is higher or younger than the sequence number of the store, right? And it's not an easy address match search, because what might happen is actually you have another X here, another store that's writing to the same place. You actually need to find the youngest store that's writing to address X that potentially matches with load address, right? And this address search is not easy also because it's really a range search. It's not really a search on a single value, because what might happen is this load may be loading 32 bytes. Well, 32 bytes may be a bit high, but for example, it's a floating point load and it's loading 8 bytes, right? And the store may be writing 1 byte, right? Now what happens, right? You can actually, it's really a range check, or it could be vice versa, right? It could be this is writing 4 bytes and this is reading 2 bytes, okay? And it could be even more sophisticated. You can have a store X, and there could be stores. This store writes 1 byte to X plus 1, let's say, and this store writes actually 1 byte to X, and this store actually loads 2 bytes, so it should really get data from both of them. So you need to determine the dependence on both. So it becomes difficult, and this is what the hardware designer needs to build actually to support out-of-order execution of loads and stores, and of course the preservation of the sequential execution semantics to the programmer. And exactly because of this reason, to satisfy the memory ordering in a single core processor, hardware designer's life becomes difficult. Okay, so preserving an expected order of operations, memory ordering, usually makes hardware designers' life difficult. In fact, that's true for instruction ordering as well, right, in a single core processor. In a single core processor, we have these large buffers to ensure that instructions are retired or committed in sequential order. We don't need those buffers. If we didn't need the sequential order requirements, basically we could execute instructions out of order and basically write them back to the architectural state of the processor and make it visible to the software, which is what writing back to the architectural state means. Basically in the order they're executed. But the order they're executed is not the sequential order, so you would not be preserving the order. But that's a lot easier to design, because now you don't need that buffering. You don't need this kind of buffering at all. Okay? Okay. So, well, I've already talked about memory ordering in a single processor just now, actually. It's really specified by the von Neumann model, and it's a sequential order. Hardware executes every single instruction in the order specified by the sequential program, right? This is true for the load and store operations. We're concerned with memory here, so this is true for load and store operations. And this is what the hardware provides, the semantics hardware provides. Out-of-order execution does not change the semantics, as I just discussed. Hardware retires or commits, which means that reports to software the results of the load and store operations in the order specified by the sequential program, right? If you violate that, then you're not obeying the semantics of a sequential ISA or the von Neumann model. There's several advantages to this, with some of which I've discussed. First, architectural state is precise within an execution, which means that at any point in time, you know what's retired and what's not executed, right? This enables ease of debugging, as I said, and this enables also ease of exception handling, because now you know where to restart an exception and how to, and also you know you have a precise state, clean state. Second, architectural state is consistent across different runs of the program also, right, in a single processor. Basically, when you run a processor once, when you run a program once, loads and stores appear in the same order. When you run it again, loads and stores appear in the exact same order. So it's easier to debug programs now. You can replicate the bugs that might happen potentially because of addresses or instruction ordering, right? Now we'll see that the second is difficult to satisfy in a multiprocessor, so we're not going to examine the second problem as much. But although that's an important problem as well, and if you're thinking about doing research projects, I would encourage you to think about doing them. The disadvantage of memory ordering, basically ensuring that preserving order, is that it adds overhead, right? It reduces performance sometimes, because these buffers, for example, if they get large, they're not easy to actually build, right? So this could actually reduce performance. At least even though it reduces performance compared to an engine that doesn't require that ordering, that doesn't require to satisfy that ordering. For example, IBM 36091 was an out-of-order execution machine. In fact, it was one of the first out-of-order execution machines of its time. And actually, I would recommend Anderson's paper, Anderson et al., that described the IBM 36091 architecture. That was written in 1965 in IBM Journal of Research and Development. And Tomasulo's algorithm also was described in this paper, an efficient algorithm for exploiting multiple arithmetic units. Again, IBM Journal of Research and Development. And this is out-of-order execution. But this out-of-order execution did not require ordering to be von Neumann ordering. Basically, you could actually retire an instruction out of its sequential order. Basically, it didn't preserve the sequential semantics. Now, the upside of this was it could be a higher performance than an out-of-order processor that did preserve the sequential semantics. Now, what was the downside? Out-of-order execution actually did not catch on at that point because this was hard to program. This was hard to debug because it didn't preserve the sequential semantics for a single thread to the programmer. So you would actually violate both of these advantages that I show over here. Architectural state was not precise within an execution. It was very hard to debug, very hard to recover from exceptions. And architectural state was not consistent across different runs of the program, which means that it was, again, hard to debug, right? So this is out-of-order. This early on out-of-order execution shows the trade-off between programmer and microarchitect very well. Later on, precise exceptions were added to out-of-order execution in, for example, Yale Pat's HPS work. Yale Pat and his students' HPS work, high-performance substrate work in Micro 1985. And as a result, basically the idea over here was to do out-of-order execution, but preserve the precise exception semantics. And almost all processors, well, all out-of-order processors that we know of today do this, right? So that's the difference. Here, the hardware design is much more expensive, and if you look at this paper, the high-performance substrate microarchitecture paper, that actually is relatively complex to preserve that sequential execution semantics because you need all of these buffers that are actually done in today's processors. Okay, let me take an aside a little bit over here and take a look at memory ordering in a Dataflow processor. In a Dataflow processor, remember, an operation, an instruction fires and executes when its operands are ready. Which means that this is true for a memory operation also, which means that ordering is really specified only by data dependencies. And whenever the data of an instruction is available, at that time the instruction can fire. Now, two operations can be executed and retired in any order if they have no dependency, right? Which means that there is no relationship between the order of a load and a store, right? Absolutely no relationship, as opposed to the single sequential instruction stream. So this is the exact opposite almost of the sequential instruction stream. There is no order except specified by the data dependencies, right? Advantage, lots of parallelism. This is high performance, right? And we've covered this in 447. And if you would like to take a look at it, 447 is a lecture that is titled Dataflow, and this is in the spring 2013. So you can search for Dataflow in the spring 2013 videos on YouTube, right? And 447 is the course name. basically this is lots of parallelism. It can exploit irregular parallelism really well. In fact, this is one of the best models to exploit irregular parallelism, and this leads to high performance. Downside, well, now it's very hard to debug, right? Basically, you have no idea of an order of the program that's currently executing. For example, if you stop the program at some point, there's no precise state, right? Some operations, because everything is dependent on the data flow order. And second, this is the first reason, which is not up there actually on the slide. The second reason is order can change across runs of the same program. As a result, this becomes very hard to debug, right? Because the order is actually sometimes the first time you run the program, maybe some latencies enable some sort of order, and the next time you run the program, the latencies are different. Maybe some values are actually in the cache now, before they were not in the cache. As a result, the second run leads to some different ordering of memory operations. Now, if you like to replicate the bug that you have, well, too bad. How do you have some order here, and you have some other order of operations here. It's very hard to reconcile these. In fact, you can have very different orders every time you run a program. As a result, this becomes very hard to debug. The second reason, the first reason that is not up here is basically there's no order between different instructions, different memory operations. As a result, whenever you stop a program, let's say you have a breakpoint in a data flow program, or there's an exception, now you have no idea which instructions have executed and which instructions have not. So that also makes it very hard to debug. So this is the extreme end. In fact, a data flow processor can be considered an extreme form of multiprocessor also, because every instruction executes independently, except for those that are constrained by data dependencies, right? So we will see that the problem that we're going to examine is a simplified version of the problem that happens in a data flow processor. And that's the problem we're going to examine. Memory ordering in a MIMD processor, multiple instruction, multiple data. In other words, multiprocessor or multi-threaded processor. Basically, we're going to assume a von Neumann model. Each processor's memory operations are in sequential order with respect to the thread running on that processor. And we assume each processor obeys this von Neumann model. But multiple processors execute memory operations concurrently. And then the key question is, how does the memory see the order of operations from all processors? Or how does the programmer see the order of operations from all processors? In other words, what is the ordering of operations across different processors? Why does it even matter? Let's first discuss this. I've already given you some reasons, but I'm going to reiterate. First, there are three reasons. First, it matters, the ordering of operations matters because it affects ease of debugging. It affects correctness, how a programmer actually can reason about the correctness of their programs. And it also affects performance and overhead. Ease of debugging, basically, it's nice to have the same execution done at different times, have the same order of memory operations. If you run program once, if you would like to say you have some memory order. If you run the program again, you'd like to see the same memory order so that you could replicate the results of the previous program, as well as you could debug the program, right? If there's a program at some point, you'd like to run that program again and you'd like to see the bug again. But the bug may not happen because the order of operations may be different when you run the program the next time, right? Okay? The second is correctness. Basically, the key question here is, if the order of memory operations is different from the point of view of different processors, can we have incorrect execution? And we will tackle this question in this lecture quite a bit. And the answer is yes, actually, by the way. You will have you can have incorrect execution, and I'll show you. And Leslie Lamport's seminal paper on sequential consistency, this paper actually has the example that I'm going to show you, although I'll give you more detail in the example. Third, ordering of operations matters because it affects performance and overhead. If we enforce a strict sequential ordering, as I showed you earlier, this can make life harder for the hardware designer in implementing performance enhancement techniques. For example, out-of-order execution. This is true for multiprocessors. I've talked about the single processor case, but for multiprocessors also. if you would like to enforce a strict sequential consistency, sequential ordering, out-of-order execution becomes hard because there's a lot of reordering of operations, and we'll take a look at that. Even caching becomes hard because if you would like to enforce a strict sequential ordering, this means that the sequential order, the order of operations coming from different processors should be visible to the memory itself. And the problem with caches is caches actually hide some of the operations that happen from the memory. That's the whole purpose of caching, right? Such that the memory operation doesn't go to memory and it stays close to the core. But if you're actually adding caches into the system, now enforcing a sequential order might be difficult because that sequential order can be observed only around the memory area. Okay? So we will talk about performance and overhead, but the main focus of this lecture is correctness. Can we have incorrect execution if the order of memory operations is different from the point of view of different processors? Now let me back up a little bit. Why does it even matter from a programmer point of view? And it matters, again, as I told you earlier, when you have shared data, when you need to synchronize. When you don't need to synchronize, maybe the order does not matter, or you can actually keep the things in order in different ways. What is synchronization? Basically, threads are not allowed to update shared data concurrently for correctness purposes, right? If one thread is adding to a linked list and the other thread is removing from it, you need to somehow ensure the threads are synchronized. Otherwise, you can get a corrupt linked list at the end. Many different kinds of corruptions can happen. So to prevent such data corruption, as well as to ensure correct execution, accesses to shared data are encapsulated in critical sections. Basically, a critical section is something that ensures mutual exclusion. Basically, access to shared data are protected via synchronization constructs, locks, semaphores, condition variables. These are different synchronization constructs that you probably know from your operating systems course. And if you haven't taken an operating systems course, I would strongly encourage you to take an operating systems course. Going forward in architecture, a lot of the interesting issues happen between the operating system and architecture interface. For example, quality of service issues, or this kind of issues happen between the system software and architecture interface. Basically, a critical section or a synchronization construct is lock, do something, unlock. Or synchronize, do something, unsynchronize. Basically, only one thread can execute a critical section at a given time. This is the mutual exclusion principle, right? The accesses to shared data should be mutually exclusive. And a multiprocessor, a key characteristic of a multiprocessor is it should provide the correct execution of these synchronization primitives to enable the programmer to protect shared data. Basically, if we would like the programmer to somehow protect shared data, the synchronization primitives should execute correctly. Otherwise, all bets are off, right? The programmer cannot even synchronize accesses from different threads to shared data. At the very least, the microarchitecture, the multiprocessor itself, should provide correct execution of synchronization primitives. So how do you support mutual exclusion? Basically, programmer needs to make sure this mutual exclusion is correctly implemented. Synchronization is correctly implemented. Basically, what does the correctly implemented synchronization mean? Basically, the programmer needs to ensure you have locks and unlocks at the right place and at the right granularity. If the programmer, for example, forgets a store, basically, this is assuming that A is shared data. If the programmer forgets to protect it, well, that's too bad, right? As a result, you may get incorrect execution because the programmer put the lock in the wrong place, whereas the programmer should have put the lock in the correct place. Well, we'll not concern ourselves with this kind of correctness in this lecture. Basically, we will assume that the programmer put the locks and the synchronization in the right place. Intuitively, they've done the right choice and they've done the logical choice, and the program is correct from the point of view of the synchronization primitives, assuming basically some kind of memory operations. We will assume this. But correct parallel programming is an important topic, is actually a very important topic, and I would encourage you to read about this, and support for actually enabling this correctness is an important topic too. It's just not the topic of this lecture. Basically, how do you enable the programmer to actually how do you make the life of the programmer easier such that they don't need to insert these locks and unlocks correctly, right? And one idea from that point of view is transactional memory, the idea of transactional memory. I'll briefly diverge here a little bit, but we'll talk about transactional memory later. this makes life easier for the programmer to actually do synchronization. Basically, instead of doing locks and unlocks on data variables, the transactional memory programming model says basically atomic. And the programmer can say atomic to a coarse-grained chunk of the program, and what this specifies is either all of this block is executed or none of this block is executed. So if there's another block, another thing that's actually storing a value into this, that's written by this atomic block, basically if there's a data conflict between this atomic block and any other operation in the system automatically detects this and ensures that this block is executed atomically, right? Or atomic can be thought of as transaction begin and transaction end. This is a very different programming model than locks, right? And it makes programmers' life easier because the programmer doesn't need to say, oh, lock this data structure with this lock that data structure with this other lock, and the programmer doesn't need to take care of these locks and their granularity. The programmer says, all the programmer says is, oh, this function that inserts, for example, a node into the linked list is executed atomically, so the system, please provide me that atomic execution guarantee. And it's, again, the hardware and the software's job to actually provide that guarantee of atomicity of execution within a transaction boundary, right? Now that makes programmers' life easier, and it actually hopefully makes it easier to implement the synchronization from the programmer level at high performance. We're not going to concern ourselves. This is part of the correct parallel programming, which is an important topic, and if you're interested, you can definitely read Herlihy and Moss's transactional memory paper in ISCA 1993, and that's a seminal paper that introduces the idea of transactional memory, at least as we know it today. Okay, so basically, even though this is an important topic, we're not going to concern ourselves with it. And actually, this has been a topic that's been around for a long time. Dijkstra, in his Cooperating Sequential Processes manuscript, which is a seminal manuscript, talked about some of the algorithms to get mutual exclusion right. How do you actually provide synchronization, do the locking and unlocking, and testing of the synchronization variable such that you get basically testing of the condition variables such that you get mutual exclusion correct, to execute correctly. And people have actually made a lot of mistakes in getting mutual exclusion correctly using semaphores as well as condition variables. And you can read that seminal paper from Dijkstra to learn more about this. But again, this is a topic that we will not discuss in this lecture. What we will discuss in this lecture is something else. Once the programmer made sure mutual exclusion is correctly implemented, the programmer actually relies on hardware primitives to support correct synchronization. Basically, if the hardware primitives are not correct, or if they're not predictable, programmer's life is tough, right? If the hardware primitive for locking is not predictable, then it's difficult for the programmer. If the hardware primitives are not designed correctly, then it's tough. The programmer cannot ensure anything. If the hardware primitives are correct, that's great, but not easy to reason about or use, programmer's life is still tough, right? So we'd like to make life easier for the programmer, and we'll see examples of this. Okay, let's take a look at an example. It's actually an example coming from the seminal paper by Leslie Lamport that you're supposed to read. And this is an example of protecting shared data. And we have actually several condition variable-like variables that's protecting a critical section that can be accessed by two processors in this case. And this is already in your slides, but I'm going to draw it over here so that we can follow it in a little bit more detail on the board. So basically we have two different processors, processor 1 and processor 2. And important operations are processor 1 executes this code. F1 is equal to 1. This is not necessarily a correct version of actually doing mutual exclusion via these condition variables, but that's okay. It is to illustrate a point. Assume that this is correct, basically. F1 is equal to 1, and if F2 is not equal to 0, then F2 is not equal to 0 means processor 2 is not in the critical section, right? Then enter the critical section. And once the critical section is done, set F1 equal to 0 to indicate that processor 1 is not in the critical section anymore. And then else there's something else, but we're not going to look at else. Else basically ensures that you retry. But that's okay. We don't need to worry about else at this point. So I'm going to erase this else, even though that will remain in your slides. Basically else, what else does is it ensures that you try again, right, somehow. So processor 2 executes the mirror image of this code. Basically, it sets F2 to 1 before entering the critical section. And if F1 is not equal to 0, then it enters the critical section. Because F1 is not equal to 0 means that processor 1 has not set this F1 variable. It hasn't entered the critical section. And once it's done with the critical section, it sets F2 equal to 0, such that some other processor can enter the critical section. And we have another else construct here, which I'm going to erase. This is executed to go back into the critical section and retry. Okay, so that's the program we're dealing with. And let's take a look at some of the operations that are interesting here. I'm going to label some of them. I need to put this over here. Basically, I'm going to label this A, B, and I'm going to label this X and Y. Okay? And that's, I guess, enough for now at least. So let's assume that this processor 1 is in the critical section. Let's start with that. If that's the case, intuitively it must have executed A, right? That's the von Neumann model. Which means that F1 must be 1, right? Because A happens before B, right? That's always true with the von Neumann model. Which means that P2 should not enter the critical section, right? Actually, I should animate this. Yes. Which means that P2 should not enter the critical section, right? Because if this is in the critical section, this must have executed A, which means that F1 must be 1 at that point, which means that P2 should not enter the critical section, right? This is basic intuition, because that's what happened before means. If B is already done, then A must have been done. If A is done, then this is not correct, right? Because this says F1 equal to 1, this says F1 equal to 0. This tests F1 equal to 0. So you cannot enter this one. So that's the basic guarantee that the programmer needs for this program to work correctly, right? So this is clear. But is that guarantee preserved? Can the two processors be in the critical section at the same time, given that they both obey the von Neumann model? The only constraint is both processors actually obey the von Neumann model, which means that the only thing that's constraining is each processor executes its operations in program order, sequentially. Same as P2 also. If that's the only thing we have, then the answer is actually yes. So you can get incorrect execution with this program, two processes that are sharing data, or two threads that are sharing data. If that's the only guarantee you have, then when this processor is in the critical section, this processor can also enter the critical section. Why? I'll show you an example. Basically, this example over here shows P1, P2, that it's communicating over an interconnection network. You can actually come up with many different examples, and they share a memory. And I don't know if I'll try to replicate it here, but not yet at least, since I'm running out of board space. But basically, you have P1 and P2, as on the slide, that are connected via an interconnection network to the shared memory. And shared memory actually stores these variables, F1 and F2, and F1 and F2. And we're going to look at an execution that leads to an incorrect result. basically this is the slide that shows the incorrect result. And this incorrect result happens because we don't provide a sequential consistency. And you will see this very soon. Basically, what we're looking at is two processors connected to a kind of two bank memory or two different pieces of memory, right? You have processor 1, processor 2, some kind of interconnection network. And what might happen is, basically, you have two pieces of memory, maybe two channels, maybe this is distributed memory, right? And F1 is residing here, and F2 is residing here. And because F2, and it turns out that processor 1 accesses F2 quickly, because it's close by, but it takes longer to access F1 because it's far away. Processor 2 can access F1 quickly because it's close by, but it takes much longer to access F2 because it's far away. So processor 1 and processor 2's updates to close by memory locations are fast, but farther memory locations are slow, right? So this is only one reason where the example that I'll show you will happen. But there could be many reasons. There could be contention in the interconnection network. It may so happen that the latencies, the queuing delays, even though the distances may be the same between processors and these memories, the latencies may make it such that processor 2's access to F2 variable is long, and processor 2's access to F1 variable is short, whereas processor 1's access to F1 variable is long, whereas its access to F2 variable is short. Okay? So let's say, let's see what happens. Basically, let's say at time t0, processor 1 executes A. This happens at time t0. And at that point, from the point of view of processor 1, A is complete. Basically, F1 is set to 1 from the point of view of processor 1. But A is also sent to memory. Basically, it takes, the processor 1 sends this to memory, such that memory gets updated, right? But it's going to take a while for that to happen. So this is time 0. And at the same time, let's say processor 2 executes X, also time 0. And at that point in time, F2 is set. F2 is complete. Basically, F2 is set to 1 from the point of view of the processor 2. And X is also sent to memory. Basically, this update F2 equals 1 is sent to memory. Okay? Now let's take a look at what happens at time 1. That's the next slide over here. And you can read the slide while I'm talking over here. At time 1, processor 1 executes B. Basically, it tests if F2 is equal to 0. Basically, it starts a load. So here, it starts a store to F1, right? And it's going to do 0. At the same time, store to F2 is started, and it's going to load 1. But the processor moves on, because from its point of view, F2 equals 1 is complete. From this processor point of view, F1 equals to 1 is complete. At time 1, this processor tests F2 equal to 0. Basically, it needs to do a load from F2. At time 1, processor 2 executes this Y operation, and it basically does a load from F1, right? Now, this load from F2 is fast from the point of view of processor 1, right? Because it's in close by memory. And this load from F1 is fast from the point of view of processor 2, right? Because it's in close by memory over here, right? So this load will come back quickly. So will this load, right? Except this store will not complete quickly, right? Because if you look at this, this store happens in F1 to F1, and that's far away from processor 1. This store happens to F2, that's far away from processor 2, right? So after some number of cycles, at time 50, this load comes back, and F2 it returns a value, right? What value does it return? Well, initially, both F2 and F1 were 0. I did not write that, right? And no one has written to them yet, right? Because processor 2's update to F2, which is F2 equals 1, is still propagating in the network. It hasn't reached this memory yet. So it's still 0, which means that this load actually returns 0. Load F2 equals 0. Right? Similarly, because this load happens much faster from the point of view of processor 2, because it's loading F1, which is in this memory, what happens in this case is this load returns after time 50. Let's say it takes 50 cycles to access nearby memory and 100 cycles to access far away memory. This load takes 50 cycles and it returns a value of 0. This is F1. Yes, processor 2 is loading F1. And it returns a value of 0 because processor 1's update, which got started at time 0, did not complete yet because it takes 100 cycles to access that. Right? So this processor also gets F1 equals 0. So now this processor got F2 equals 0. This processor got F1 equals 0. And the test is not true anymore. Which means that both processors enter the critical section. Right? Now at time T51, both processors are now in the critical section. Now this is bad, right? The programmer did the right thing and synchronized these critical sections, but the processors entered the critical section at the same time. Basically, mutual exclusion principle is violated. Well, later on, at time 100, what happens is this processor store to F1 actually gets completed, so F1 gets the correct value, 1, and at the same time, this processor store to F2 gets completed, so F2 gets 1, but it's way too late. Why? Because these processors actually already tested the wrong value and got the wrong value from memory. And as a result, they both entered the critical section. This processor got the wrong value from memory, well, wrong from an intuitive perspective, from a memory ordering perspective, from F1. And this processor got a value 0 from memory. They didn't see the updates that happened to respective variables. This processor, even though this processor updated F1 internally, this processor did not see the update that happened to F1. Same as, even though this processor 2 updated F2, processor 1 did not see that update. That update was not visible to processor 1. Or at least that update became visible way too late, right? When it needed that data, that update was not visible. As a result, the ordering was not consistent because these processors did not see the updates to the memory locations in the same order, or did not see the same order of memory operations. And that's exactly the problem. Let's take a look at the problem basically in another way. These P1s, let me list you the P1's view of memory operations first. And this is the next slide over here. Basically, from the point of view of P1, what happened is A was executed first, and then B was executed next. And later on, after some point, X completed, right? And the next was executed. So A was executed at time 0, B was executed at time 1, or actually time 50, right? That's when the data actually returned. And X was executed at time 100, right? On the other hand, from processor 2's point of view, X was executed at time 0, Y was executed at time T50, and basically, I should say A here, A was executed at time T100, right? So what happened is an inconsistent view, right? This doesn't satisfy the happens before relationship, right? Because if you look at this, according to this processor, A happened before X, but according to this processor, X happened before A. That's the inconsistent execution. And as a result of this inconsistent execution, because the two processors saw different orders of execution, they both went into the critical section at the same time. So you got the incorrect execution because of that reason. And the problem is, fundamentally, the two processors did not see the same order of operations in memory. Well, how can we solve the problem? Basically, the idea is sequential consistency, and this is Leslie Lamport's 1979 seminal paper. The key idea is very simple. Make sure that all processors see the same order of operations to memory. It doesn't matter what order that is, but ensure that the order is exactly the same as seen by different processors. So this should not happen. A happened before X, and X happened before A. Should not happen at the same time. Both processors should see A happen before X, or X happen before A. It cannot be both for different processors. It cannot be different for different processors. Basically, the idea is all memory operations happen in an order that is consistent across all processors. This is called the global total order. You have a total ordering of all memory operations, reads and writes, loads and stores, and that global total order is the same across all processors. And the assumption is that within this global order, each processor's operations appear in sequential order with respect to its own operations. So sequential semantics within the processor is maintained within this global order. That's an assumption. And we're going to assume von Neumann model, as I said earlier. So that's the idea of sequential consistency. Basically, this is described in the reading that you have, less than 2 pages, remember? It's always good to read papers that are short and that actually prove a seminal point. Lamport defined sequential consistency as a multiprocessor system is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order, what I said before, and the operations of each individual processor appear in the sequence in the order specified by its program. And that's the von Neumann sequential execution semantics. So this is a memory ordering model, or memory model. This is specified by the ISA, and many ISAs specify it. And this is, again, a programmer's abstraction. If you think about it, you can think of programmer's abstractions and memory as a switch that only services one load or store at a time. That's how you can actually enforce, think of sequential consistency from any processor, right? All processors see the currently serviced load or store at the same time. And each processor's operations are serviced in program order. Basically, that's what sequential consistency means from a programmer's abstraction point of view. Basically, here, the problem was the memory was not a switch. We're going to replace this memory as a switch. Okay, I'll do this a single connection for now. Basically, at any given point in time, only one processor can access the switch, and that processor's operation is visible to everyone else. And if later this processor can access the switch, and that processor's operation is visible to everyone else. Basically, memory is a switch connected to many processors, and only one processor can access memory and complete its operation before another processor can do it. Read or write. That's the idea. This leads to sequential consistency. This is very similar to sequential instruction execution, right? It's really sequential memory execution, if you will. Very similar to the von Neumann model applied to memory. Memory executes operations sequentially coming from any processor. And all processors see that sequential view. Okay, so in this case, there are many potentially correct global orders. Basically, what is a sequentially consistent operation order? Basically, the operation order that satisfies what I said earlier. And in this particular example that I showed you, there are many correct global orders. And some of them are, basically, you need to ensure that this cyclic dependence does not happen. A happened before X, X happened before A, doesn't happen. So A, B, X, Y is a correct order. A, X, B, Y is a correct order. Right? A, X, Y, B is a correct order. And X, A, B, Y is a correct order. Right? And then X, A, Y, B is a correct order. And X, Y, A, B is a correct order. This is all sequentially consistent. Basically, you can serialize this. Whereas this, you cannot serialize. If you have a loop, you cannot serialize those operations. Okay? And which order is actually observed at runtime depends on the implementation and the dynamic latencies. It really depends on how long it takes to do these operations. As long as you guarantee sequential consistency, you'll get one of these orders. But which order is preserved really depends on the implementation. So what are the consequences of sequential consistency? Let's draw some corollaries. First, within the same execution of the program, all processors see the same global order of operations to memory. Which means that there is no correctness issue that we've seen with this code, right? No correctness issue. The code will execute correctly. And the second thing is this satisfies the happen before intuition of the program. Basically, you don't go crazy trying to figure out what happened before what. Do I have a cyclic dependence? If you don't have sequential consistency, you could go crazy, right? Because you could have cyclic dependencies. So this makes programmers' life easier. Now there's another corollary. Across different executions, different global orders can be observed. And this is unfortunate because sequential consistency's goal is not to provide that. Across different executions, you can have different global orders, right? In one execution, you can have A, B, X, Y, which is sequentially consistent. In another execution, you can have X, Y, A, B, which is also sequentially consistent. Now, both executions are correct from a sequential consistency point of view. But the problem is, this makes debugging still difficult because if you want to exactly replicate one execution when you run the next execution, for debugging purposes, for example, this becomes difficult because the order now changes. As order changes across runs, some bugs may be exposed, right? Maybe the bug happens if the order is X, Y, A, B, but it doesn't happen if the order is A, B, X, Y, right? Now this is a bug that's at a higher level. Maybe it's a synchronization bug, right? So this is tougher to do. This cannot be done with sequential consistency. Basically, here you really need to preserve the order across different executions. And to be able to do that, you really need to provide deterministic execution. What does deterministic execution mean? Regardless of when you execute a program for a given input set, you always get the same ordering of operations, right? Now this is tougher to do, and people have looked at this problem, and one way of providing deterministic execution is memorize the order in one run and replay it in the next run. It may be tough to provide this deterministic execution because the order of operations actually depends on the latencies, right? Latencies in the system. It could be dependent on the congestion, right? The order may change between one execution of this program and the next execution of this program because what might happen is there's more congestion in the network because some other application was running in the was not running in the first execution of the program, but it starts running in the next execution in the system, right? And you cannot control that application, right? It's very difficult. Even within an application, in the first, there may be some caching behavior. Latencies may be shorter because things are cached in the first execution, but in the second execution, it so happens that it doesn't get cached. Why? Because there's some system level issue that has destroyed the cache, that has kicked out blocks in the cache, right? So this is a harder problem. Basically, sequential consistency doesn't solve that different execution problem, having different global orders in different execution. You need to provide deterministic execution. I'd be happy to provide you readings. This is also an interesting research topic. And if you're interested in doing research in that area, I'd be happy to provide you readings with that. So, are there any issues with sequential consistency? It's a nice abstraction for programming, but there are actually two issues. One is too conservative ordering requirements. Do you really need ordering of every single operation to be global, to be part of a total global order that's visible to all processors? Is this not too strict? What if you have actually loads and stores that have nothing to do with shared data or synchronization? So we're going to visit that. And the second is, again, because of this too conservative ordering requirements, sequential consistency limits the aggressiveness of performance and enhancement techniques. For example, out-of-order execution. Now you cannot, even if you do out-of-order execution, you have to obey this globally consistent total order, right? So you cannot basically load instructions, load from memory in the order, in the data flow order, right? This makes life harder, basically. Basically, this leads to the question, and also caching as well, right? If you actually have caches over here, if you want to have the memory to see a global total order, if that cache caches a value, now you need to somehow make that visible, make that address that's cached visible if the processor accesses it. Otherwise, you won't have a total global order, right? That's why sequential consistency is very strong. The total global order requirement is actually too strong. Do we actually need a global order across all operations and all processors? And the answer is no, actually. But this makes programmers' life a little bit harder. Basically, how about we have a global order only across all the stores, right? Instead of having a global order only across all the memory operations, loads and stores, how about we do it only for stores? Because maybe it's only for stores that actually matter, right? And I'd like you to think about that. This leads us to models like total store order memory model or unique store order memory model, which is employed in many processors actually. x86, for example, has a total store order like memory model, which basically ensures that all stores are ordered in a total global order, but not necessarily the loads, which gives the hardware some flexibility, right? Now the hardware can do out-of-order execution easily without ensuring that the operations that are done out of order actually satisfy a sequential consistent view. Because only the stores need to satisfy a sequentially consistent view in that case, right? Total global order. Okay? How about enforcing a global order only at the boundaries of synchronization? If there are periods where you don't need to synchronize, why do you care about a global order? Why do you care about any order between different threads? These threads are totally independent in that case, right? So why not enforce this global order at the boundaries of synchronization? Maybe this leads to models like relaxed memory models, acquire-release type consistency models. For example, maybe over here you have an acquire operation and you have a release operation, maybe not exactly here, but during the lock point. And only these need to be sequentially consistent, right? Acquire, release. Okay. It won't work exactly the way I showed it over here, but this is just to give you an example, right? Basically, you can relax this global order requirement, total global order requirement, by ensuring that there is some global order across some of the synchronization primitives, right? At the boundaries of synchronization. So we'll get back to this with weaker consistency models in a little bit. But basically, performance enhancement techniques that could make SC implementation difficult are twofolds. One is out-of-order execution, and the other is caching. And I've already talked about this briefly. Let me also cover it again briefly. Loads happen out of order with respect to each other and with respect to independent stores if you have out-of-order execution. So that basically simply changes the global order requirements, right? They can happen out of order, and within a processor, you can actually provide the illusion that they actually happen in order, but they happen out of order in memory if they're actually sent out of order from the processor. And now that makes it harder to provide sequential consistency, because what might have happened is this load actually, this processor, for example, does one of the loads earlier, for example, load of F2 earlier than the load of than the store of F1, and as a result, what might happen is it can see the value 0. This processor may do the load earlier, and it can see the value of 0. And as a result, they can both be in the critical section, right? If out-of-order execution is not implemented correctly to support sequential consistency. And I'll let you think about that. Caching also is another problem. Basically, a memory location is now present in multiple places in the system. And if caching prevents the effect of a store to be seen by other processors, as a result, you can get incorrect execution again, right? Basically, you will need to, either you get incorrect execution or you get rid of the issues in caching, right? Basically, if this processor writes to location B, this write to location B may not be visible because it's doing it on its own cache, right? For example, this processor is writing to location F2. The same issue persists, right? And this processor is writing to location F1. And caching is great, right? Because what caching does is it keeps locality. Now, if both of them are writing to F1 and F2 in their private caches and they're continuing execution, now what might happen is they will eventually get into the critical section again, because this F2 and F1 changes do not get propagated to memory, right, where you enforce the global order. So caching actually, if you want to get performance enhancement with caching or outward execution while providing sequential consistency, implementation actually is difficult. You'll need to ensure that sequential consistency is maintained. At the same time, you get high performance with caching and out-of-order execution. And that's one of the reasons why people have looked at weaker consistency models. And I'd recommend you to look at the Louis Cézé paper related to sequential consistency and out-of-order execution and caching techniques. And they have a solution, which we will briefly discuss toward the end. So what is weaker memory consistency? Weaker memory consistency was motivated by the understanding that the sequential consistency model is very strong. Too strong because it it makes the hardware complexity harder, especially when you want to implement hardware performance enhancement techniques like caching, prefetching, out-of-order execution. And also, maybe it's too strong, right? Maybe it's really not needed. In weaker consistency models, the ordering of operations is important when the order affects operations on shared data. That's the realization. Which means that the ordering of operations is important when the processors need to synchronize to execute a program region. Program region could be a critical section, for example. And weak consistency, the idea is programmer specifies regions in which memory operations do not need to be ordered. Once the programmer specifies that, the hardware doesn't need to provide any order during those regions, right? And the programmer provides memory fence instructions to delineate those regions. For example, this acquire can be thought of as a memory fence. And there could be another memory fence over here. Again, this is just an example. I'm not giving you the correct program. But, and all memory operations before a fence must complete execution before the fence is executed. And all memory operations after the fence must wait for the fence to complete. Basically, this enforces serialization of all memory operations in the system. That's how you can achieve the effect of sequential consistency, because when you get to a fence, it's basically like a precise state, right? All memory operations before it must be complete, and no memory operation after it can be started. And all memory operations after this fence must wait for the fence to complete. So this is a synchronization point, serialization point. And once you have this, and once you also ensure that fences complete in order, so you have fence 1 over here, fence 2 over here, and fence 1 over here, fence 2 over here. Now you get sequential consistency across fences, right? And that's the idea of a weaker consistency models. And all synchronization operations act like a fence. Basically, you can have a fence here, you can have a fence here. These are kind of synchronization operations, right? They act like a fence. And this is how you get a weaker consistency model. Now, obviously, it's harder for the programmer to do this, right? So we'll run into some trade-offs. And I'd encourage you to read Korosh Garchorlu's paper in ISCA 1990. And at the same time, in the same ISCA, there's a paper by Sarita Adve and Mark Hill. The paper is called Weak Ordering, a New Definition. And that also talks about weak consistency, very similar to Korosh Garchorlu's work. And this should be part of your reading as well. Okay, the trade-offs, basically there are advantages to this, right? There's no need to guarantee a very strict order of memory operations with a weaker consistency model. Now there are benefits to this. This enables a hardware implementation of performance enhancement techniques to be simpler. So the caching, for example. You don't need to, out-of-order execution, for example. You don't need to satisfy an order between the fence operations. Only at the fence operations you need to serialize, right? And it can be higher performance than stricter ordering, assuming you don't do any fancy techniques for stricter ordering, right? Basically, it can be higher performance because the hardware can exploit the parallelism. It doesn't need to serialize the memory requests. Okay? The disadvantage, there's more burden on the programmer or software, right? Now the programmer or the software needs to get the fences correct. Before, they just needed to get the synchronization operations correct and rely on sequential consistency. But now they need to get the fences correct. So programmer's life is much tougher. As a result, these models are harder to reason about. And this is an example, another example of the programmer microarchitect trade-off that we started covering in the beginning of this lecture. Basically, weaker consistency models make the life harder of the programmer, but they make the hardware designer's job easier, right? On the other hand, a sequential consistency model makes life easier for the programmer, because the programmer doesn't need to reason about the ordering of fences now, or where to insert fences even, whereas it makes the job of the hardware designer harder, because the hardware designer has to provide high performance while preserving the sequential consistency semantics. Okay, so we've actually talked about this earlier. One good research project idea would be, how do you actually make performance enhancement techniques that keep the sequential consistency, but while designing these techniques to be easy to design? How do you actually make the SC implementation, sequential consistency implementation, more amenable for the design of these performance enhancement techniques? And I'll let you read about this, and I'd be happy to provide some readings on this. That's the end of this lecture, but let me cover some of the readings. We've talked about Lamport's classical reading. We've talked about Garachorlu's classical reading on weaker consistency models. And I've also recommended, let me actually clean up. But Lamport's reading actually introduced sequential consistency, as I told you. Garachorlu et al. From Stanford introduced what they called release consistency, which is a form of weak consistency. And at the same time, Advey and Hill, in the same ISCA 1990, introduced weak ordering, basically, which is another form of weak consistency. And this is in ISCA 1990, weak ordering, a new definition is the name of the paper. I recommend you to read that also. Garachorlu has a paper in International Conference on Parallel Programming, Parallel Processing, sorry. Two techniques to enhance the performance of memory consistency models, and this is a good read also. Cézé's paper, Bulk SC, looks at bulk enforcement of sequential consistency, and the idea over here is to reduce the overhead of synchronization by ensuring that basically you have a program, right? You have load, store, ... load, store, ... load, store, ... whereas another program also in another thread, store, load, ... Basically, sequential consistency as we know it enforces a sequential ordering after every operation, right? Cézé's insight in that paper is basically, why don't we divide the program into atomic blocks and maybe just randomly chop it off and ensure sequential consistency at this coarse grain. Basically, it's a coarse-grained enforcement of sequential consistency. How do you do that? Well, one way you could do that is actually, you basically keep track of which addresses were touched in this block, and later on you also keep track of which addresses were touched in the block, and if there's any conflict, then you ensure that the blocks are serialized. You re-execute one, for example. If there's no conflict, then maybe it's okay to execute. Basically, the only thing you need to do is to keep the ordering of the blocks, right? That's all you need. Instead of keeping the ordering of individual instructions, keep the ordering of the blocks sequentially consistent. So don't forget about the data conflict. That's really about transactional memory. So I take it back. But instead of having fine-grained enforcement of sequential consistency, instruction by instruction, coarse-grained enforcement of sequential consistency does it block by block. And in the end, it's the same thing, right? If this block comes after this block, now you preserve the sequential consistency, right? Then the key question is, how do you form the blocks and when do you terminate the blocks? You can take a look at the ISCA 2007 paper related to that. And there's also Amdahl's paper that I referenced here, which you should have read by now, and Dijkstra's cooperating sequential processes. And there are many, many other references actually that I can provide. I'd be happy to provide them if you'd like to do a project related to this. And these are the related videos. You can find related videos from 447. If you do not know precise exceptions and state maintenance, I would strongly recommend you to watch that, because that handles the basic ordering issues in a single core processor. And that's all I have. And actually, there's a related question apparently in an exam, in question 4 in last year's 447 exam, and it's linked from here. And there may be many, many interesting questions related to consistency, and I'd encourage you to think about that. One last parting thought. Consistency issues arise in distributed systems as well, right? For example, how many of you had Windows open for Gmail on computers that are close by? Well, maybe several of you. How many of you have received an email on one of those windows but did not see the email on the other one? Right? I've seen that many times. In fact, I've written a draft here that doesn't appear here, and vice versa. Right? I've actually deleted emails here that did not get deleted over here. Right? And I've written because they're into ordering issues. Well, this is actually a consistency problem, right? You have these mailboxes that are in different places, and the ordering of operations may be different to these mailboxes. And that's essentially what you're seeing in a distributed system as well. So having this consistency is interesting, and sometimes basically when do these updates get propagated and become visible, in what order, is interesting. And systems today, some of the distributed systems, there's a discussion of eventual consistency, which is actually almost no consistency at all. Basically, eventually at some point, consistency is guaranteed. The updates will propagate, and everything will be consistent. And this is an interesting form of consistency. And if you're interested in this, I'd be happy to talk about it and potentially propose research ideas to you. Okay.